Welcome to the new CloudStation version. We are going to discover all the new features this new version of CloudStation has to offer. All modules will be used to process a dataset acquired on a golf course with a YellowScan VX2300 and a single Sony a7R III nadir camera. Let's get started. Let's start by creating a new project. In my project folder, right here, I have 3 folders corresponding to each flight. Each folder contains all the laser data, as well as my SPET and my images. CloudStation will automatically detect all the flights in the subfolder and suggest all of them in a small list right here. Because I want all my flights, I can go on and create my project. As you can see, there is quite a lot of changes to the UI of CloudStation. Although some things are familiar, some other elements have changed quite a bit to accommodate for the multi-flight handling of this new version of CloudStation. Let's start by selecting more flight lines on each flight. The new timeline gives you more details about the time. You can zoom out and zoom in, but also pan on the timeline to have a more precise manipulation of your strip. Here, I'm pretty satisfied with the distance, so I'm just going to hit save. Now that I'm satisfied with all my strips, I can start to select all my flights and bring in the correct parameters for each of them. Here, I just want to verify that the LiDAR profile is the correct one. Everything is in order. All my flights are ready. All my strips are ready. I can just go on and process. As the extraction progresses, you can see that each strip is turning into an individual progress bar. Because I have everything selected, I have the total number of points being updated almost live. Because I have the option turned on, CloudStation will first generate a subsample of my point cloud, so it have a quick display. Then it will generate the full density for my point cloud. My point cloud is now fully ready to be displayed. If I zoom in, I have my entire resolution. I can hide my trajectories by clicking on this point. Or if I just want to hide one flight, I can hide the trajectory of this specific flight. I can change my cloud color by clicking on the color icon right there. A new menu opens and I can change the color for my point cloud. Here, this is the intensity value. I can also combine different colors and change the intensity of each color. The second menu allows me to filter my data. Only the data within my filter will be displayed. Now, let's move on to strip adjustment. Strip adjustment is complete, and we can see there is an improvement in the overall precision and accuracy of the system. Now that my point cloud is strip adjusted, I can either go to the terrain module or the colorization module. Let's do terrain. The terrain module allows you to extract the ground from the non-ground, classify your point cloud, and then generate different digital models. Let's get through the settings and see what we can do to extract our ground in this dataset. The first setting is the object inner size. We want to measure the diameter of the largest data gap in our point cloud. In the north of the dataset here are some housing. This is probably going to be the largest data gap in our dataset. The trick is to flip your point cloud upside down and to check where you should have some data gaps. It looks like these houses are going to be the largest ones. I can use the measure tool to measure the size of the large holes that these houses generate. In a few clicks, I can see that I have about 13 meters of a gap. So to be safe, I'm going to put 15 meters in my object inner size. The second parameter is steepness. The steepness corresponds to how rough the terrain is going to be. Here, it's pretty hilly, although there are some steeper areas right there. So, in that case, I'm going to pre-select steep. I could enter manually a value somewhere in between hilly and steep. The next parameter is the object minimal height. This corresponds to the smallest object that will be considered non-ground. Here, 15 centimeters is good. The point cloud thickness is a preset we use, but you can enter your own value. It is the expected point cloud thickness to be classified as ground. Let's use these default values. Let's classify. Our classification is complete. I could display my cloud with the classification option to see everything. In gray, we have the ground. In orange is the non-ground. I can filter my cloud depending on the classification. If I remove anything that is not ground, I can see all the points that make up my ground here. Seems pretty good to me. Let's move on to the colorization. The colorization module has more options than the others. However, it remains pretty simple. The first one is the refinement of your camera calibration. By default, YellowScan provides you with a camera calibration for your unit if you purchased one. However, you can refine the camera calibration for your specific flight to have better alignment for this flight. Two colorization methods are available, using the closest image available or the median color from all the images that see a given point. Lastly, the detection of occlusions will use the LiDAR point cloud to check if a point sees a given photo and use this color value or not. Now, for each of my flights, I need to bring in my image directory as well as my images timestamps that I did in POSPAC. Notice how my photo ID list was automatically detected. That's because I put it in the same folder as my images. Now, I have to do the same thing for all my flights. Let's do a median color. Obviously, Each option selected here will increase the processing time. However, I want the best result possible, so I'm using the detecting of occlusion, and I'm refining my camera calibration. To refine my camera calibration, it is best to have at least a crossing line for each flight. Here, for this flight, my pattern was like this, but I added a transect at the end. Same thing for the second flight and for the third flight. Let's colorize. Now that the colorization is over, we can use the color to display all the colors in our point cloud. The grayed areas correspond to areas where either no photo was covering the area or areas that were occulted. Let's hide the trajectories to see the point cloud better. And that's it. We can now move on to the export section. You can export either a point cloud or multiple types of digital model. When exporting a point cloud, you will need to give it a base name. By default, we are exporting every single strip as a separate file. You can choose to merge by strip or by flights. When exporting, select the coordinates reference system that you want to use. And by default, the export folder is located at the root of your project. If you have classified your point cloud using the terrain module, you can export ground classes or even only the ground. You can export colors if you have colorized your point cloud, but if you haven't, by default, it will use the colorization from the Z value. When you're ready to export, press export. If you want to export a digital model, you have the choice between a DSM, a DTM, and a DHM. When exporting a DTM, you have additional options. First, obviously, is still your coordinate system in the output folder, as well as the name you want to give it. For the DTM, choose your pixel size and max hole size. The max hole size is the largest data gap that will be filled with your Z value. Choose between the minimal Z value, the mean Z value, or the maximum Z value in your pixel. You can also export a hillshade. When you export a hillshade, you can choose between a unidirectional lighting. In that case, determine where your single light will be located. And when using multi-directional, you just choose the altitude where all the lights will be. Whenever you're ready, hit export.